There we go. Okay, we're doing U subs. So before we actually begin, the little part at the top is separate from what we've been doing, or separate from what we're going to do, kind of. The family of all antiderivatives of the function is the indefinite integral. A definite integral has bounds, goes from point A to point B. You will get a specific numeric value. An indefinite integral has no bounds, and it's the general solution. When you do the antiderivative plus c, that is your solution to an indefinite integral. So that's one of the major changes we're going to have now. It's not every integral will have bounds, will have a numeric answer. Some will be algebraic solutions. Most of them today will actually be algebraic solutions. So the integral of f of x dx is f of x plus c. Do not forget your plus c on this test coming up. Oh my God, that'll kill you. You have to remember it on that one because a lot of the answers, if there's no A and B, if there's no bounds, you have to have that plus c on there. Okay. Now, you've been doing antiderivatives for a while now to solve integrals. Most of those have been fairly straightforward, not too complicated equations that you're dealing with. That is about to change. Let me front load this lesson by saying the most recent method that you learn for solving integrals is not necessarily the best one nor the first one. Normally in math, when you learn how to do something, you go, oh, now I can do it this way, and it will always work no matter what. Integrals are not like that. You want to try to do the simplest possible solution first. You want to try to do a straight up antiderivative if that's possible. If you see a polynomial, you just take the antiderivative and go from there. Do not try to do something more complicated. Try the easiest method first, and then step your way up. We're going to do U subs today, and later on at the end of the week, we're going to learn how to do UV subs. They're actually so complicated, you actually have to add something else to substitute. You do two substitutions there. You do not want to start and try to answer every problem on the test. There's somebody who always does, using the last thing we learned, because the last thing we learned is usually what always works when you're taking a math test. It does not work that way with integrals. You have to look at the problem and decide, based upon the problem, which method to use, because some are easier than others. If you try to do straight up antiderivatives when you should do a U sub, it won't work. If you do a U sub when you should do a UV, it won't work. When you do a UV when you're supposed to do a U sub, it won't work. So they're not interchangeable methods. Okay. Now, this is what we're dealing with. Oh, and there's something else that's mentioned on here I did want to talk about. Table of integrals. There is a fallback that always works. In your textbook, the last, near the end, one of the appendices in your textbook is a table of integrals. It is filled with the integrals, with the antiderivative solutions for all kinds of integrals. It's like 5 pages of antiderivatives for integration. That is like the fallback. Oh crap, nothing I know works. I look forward to hearing my table of integrals, and it'll work for you. I think there's like 100 and something, 140, 150, somewhere around there, integrals that are solved, general solutions to integrals in the back of your textbook. You already know how to do most of them are in there. So it'll have like the integral of the integral of the sine is the negative cosine plus c, and it'll have all that kind of stuff. That works great. Sometimes they're just not there. So what we do is we look at this problem here. This is, remember, there's no product rule for integration. Okay, there's no chain rule per se. This is about as close as you come to the chain rule. what you're looking at is I can't just do an antiderivative because I can't take the antiderivative of the sine and the antiderivative of e to the cosine. It just doesn't work. So what I have to do is I have to do a substitution. This is a very nifty trick. The most difficult part about doing a U sub is deciding what your U sub is going to be. What portion of that you're going to pick to substitute for. There are a few basic, I don't want to say rules because they're not really rules, but ones you want to pick. If you have an exponential, we have an exponential. I let my u generally be whatever my exponent is. In this case, cosine. Now what's going to happen is when we're going to substitute that out. We're going to get rid of the cosine. We're going to get rid of any x term. We're going to do a substitution. There will no longer be any x's or dx's in our integral. So I let u be cosine of x. Then I have to take the derivative of that. The derivative of the cosine, du, would be negative sine x dx. I'm going to replace cosine with u. Yes?
So the problem is it's sine of x times?
Sine of x times that, yeah. Let's imply parentheses around here. Yes, that's a good question. Good question on that. Maybe I should go back and fix that. Try to do that before I save it for next year. Okay. So I want to replace everything that's there with something new. Now, I can replace cosine of x with u. And then I look, okay, I want to put du in there because I'm going to be doing it in terms of u. I need du, not dx. And I go, okay, well, du is equal to negative sine x dx. Do I have negative sine x dx? Almost. I have sine x dx. I do not have negative sine x dx. Not a problem. Negative du equals sine x dx. And now I can do my substitution. Cosine x, cosine x. Negative sine x dx, or sorry, sine x dx, sine x dx. So that means this integral is equal to negative e to the u du. Negative du replaces sine x dx. U replaces cosine x. This I can take the antiderivative of very easily. What is the antiderivative of negative e to the u? Negative e to the u. Yeah, that's an easy one. Now, what do I have to do when I take the antiderivative? Let's see. There's a problem with my answer, though. What's the problem with my answer? It's u. What do I start with? X. Not a big deal. I just take u, replace it with what I did for my substitution. So my final answer is negative e to the cosine x plus c. Start with x. I need to end with x. The idea is we take a complicated integral, difficult to solve on its own, and make it into a simpler problem. That's the idea behind substitution, is we're trying to make it into a simpler problem. The antiderivative of e to the u, that's very easy to do. Okay? This, complicated. This, easy. That's the whole idea behind u subs, is to take something complicated and rewrite it as something easier that we can do very, very easily. Yes? Yeah. Just like take the antiderivative of something dx, the dx goes away. Same idea. Okay. Questions so far? So, exponents. Good thing to substitute. Get rid of the exponents. Okay. Same concept. The original problem, not so easy to do. The integral of x squared 5 plus 2x cubed dx. You could try to rewrite it as to the 1/2 power, which really you're going to have to do anyways. You can't do antiderivatives of square roots. You have to rewrite them as exponential powers. But really, that's not going to buy you anything. And then trying to take the x squared and stick it back inside the 1/2 power, it's still not going to help you out any. Okay, you can do that. Just make it x to the 4th power when you multiply through. If you pull out a square, you have to plug a 4th back into a radical. You can do that. It's generally not advisable. So I want to do a substitution. What do you think I should let my u be? 5 plus 2x cubed. Generally, everything inside the radical. That's a good starting point. It's a good starting point. It's not guaranteed. And if it doesn't work, you can always try something else, but that's a good one. Exponents. Good to replace the exponents. That's usually very helpful. Inside the radical. That's usually very helpful. So if I let u equal 5 plus 2x cubed, du would be, well, the derivative of 5 is 0. The derivative of 2x cubed would be 6x squared dx. Do I have a 6x squared dx? No, I do not. I do have an x squared dx, so I have most of that. I just don't have the 6 of them. So what do? Multiply both sides by 1/6. 1/6 du is equal to x squared dx. And now I can do my substitution. So this gives me the integral of 1/6 u to the 1/2 power du. So I did two things here. One, I replaced 5 plus 2x cubed with u, but I also rewrote the square root as a 1/2 power. Okay. Now, something that might help when you're doing your antiderivatives and you're trying to solve this problem. Remember, you can pull constants out of the integral. And do your antiderivative with what you got there, and then take that and multiply it times the constant you pulled out when you go to your final answer. Sometimes it really helps if you don't have to think about that constant while you're doing your antiderivative. Sometimes it really helps when you're trying to do that. Okay. So this would be equal to 1/6 times my antiderivative of u to the 1/2. Well, what do I do to a power? I increase the power by 1. So I have u to the 3/2. And then, like I said, I can ignore this out front. So what do I have to have here to counterbalance bringing the power down out in front? I have to have a 2/3 plus c. Now, technically, that 1/6 is times the c as well. But what is 1/6 times a constant that we don't know? It's still a constant we don't know. So it really doesn't matter what we call that constant. You don't want to do 1/6 c. It's irrelevant. Or I should say it's redundant. Because if it's something we don't know times 1/6, it's still something we don't know. It's just a constant. Okay. Now, I need to clean this up here. So 1/6 times 2/3 gives me 1/9, right? 1/9. And u is no longer u. It is now back to the original 5 plus 2x cubed to the 3/2 power plus c. Now, I should rewrite it as a radical, but realistically, I don't think that's going to be an issue. You do need to know that you have both as radical form an exponential form, you need to be able to go back and forth between them. I'm trying to recall for AP, this would be a multiple choice question. And from the examples I've seen, they would actually have the answer like this in exponential form rather than radical form. I prefer going back to anything that's original, but I'd probably go ahead and take this on the test. Okay, questions so far? So far we've done U subs for things that are exponents, things that are inside radicals. Now we have this one. Now remember, you always want to do whatever's easiest first. Is there an antiderivative for the cotangent? Is there something I take the derivative of that gets me the cotangent? There is an object that I take the derivative of that gives me the cotangent times the cosecant, but not the cotangent by itself. So when I look at this, a number of the most common things that students would want to do would let u be 7x, and then du is 7dx. So I get 1/7 du equals dx. And this is not necessarily a bad thing. Kind of go with me here on this one. So this would be the integral of 1/7 cotangent u du, but that's not really helpful at all, is it? It's really not helpful because I still have the most difficult thing to do. That cotangent is still there. And that cotangent is what's screwing me up. So I don't want to do this. But I tried. So I want to do something else that's going to work better. Well, here's what I like about trig functions. You can rewrite them into something of a different form. The cotangent is also known as the cosine over the sine. And then here's what you want to ask yourself, and this is what's true of all U subs. Does the derivative of part of my integral give me the rest of my integral? And if we go back and look at these other two examples, the derivative of part gives me the other part. The derivative of the cosine gave me the sine. So substituting for u gives me the rest of it. The derivative of this part gives me that. That's what has to happen. The derivative of part of it lets me do the other part. There we go. Does the derivative of one of these give me the other one? Yeah, actually either one of them, doesn't it? The derivative of the sine gives me the cosine. The derivative of the cosine gives me the sine. But that's not really the sine, is it? That's really 1 over the sine, is it not? Does the derivative of the cosine give me 1 over the sine? No, but the derivative of the sine does straight up give me the cosine on its own. So if I let u be the sine of x, sine of 7x, du would be 7 cosine of 7x. So let me write that a little neater. Following the chain rule, right? The derivative of the sine times the derivative of what I'm taking the sine of. And that's where the 7 comes from. Now, I don't have 7 cosine x, but I do have cosine 7x, so 1/7 du is equal to the cosine of 7x dx. Cosine of 7x dx. That's what 1/7 du is equal to. So I get the integral of 1/7 du, and then the sine of x, that would be 1 over u. What is the integral of 1 over u? ln of u. So this would be 1/7 natural log of the absolute value of u plus c. And you want to do the absolute value because you're not allowed to take the natural log of 0 or a negative number. And I don't know if it's positive all the time or negative all the time. I really can't tell. So what I do is I put an absolute value sign around when I'm taking the natural log of when I do my antiderivatives to cover my butt. Now I know I'm okay as long as u is not 0. Because you can't take the natural log of 0, but you can't take the natural log of negative. But the absolute value handles that part of the antiderivative. Now, am I done?
No.
No, because what did I start with? X. I have to have x for my final answer. Oops, cosine, yeah. Sine of 7x plus c. So we've done 3 of these so far. We have let u be the exponent in an exponential. We have let u be what's underneath the radical with a radical expression. We have let u be a denominator. That kind of steering you down the road of what you should be thinking about when you're doing your u subs. Because that is the most difficult thing, is what should u be. So much so that at the beginning of your homework, it actually tells you what your u is. Okay? First few problems.
Wow.
Okay. I want you to attempt this one. So we do our substitution. That is recommended here. First, power rule formula, cosine squared dx would be equal to 1 plus the cosine of x, sorry, cosine of 2x, my bad. 1 plus cosine of 2x over 2 dx. And you know what? I'm going to pull out a 1/2 and rewrite this as the integral of 1 plus cosine 2x dx. You don't have to do a u substitution for everything. And you don't necessarily have to do a u substitution on this one at all. If I were to do a u substitution, my u sub would be for 2x. It would not be for anything else. If I let u be the cosine of 2x, do I have a sine of 2x in there? I do not. You do not need to do what we've been doing just because it's what we've been doing. That's part of what this problem is about. To illustrate my point is you don't always have to use the most difficult thing we just got done doing to solve an integral in particular. I can just do the antiderivatives straight from here. Now, some of you are still struggling with the antiderivative of the cosine of 2x because of the 2x in there. I can do this as 2 separate integrals. 1/2 integral of 1 dx plus 1/2 the integral of the cosine of 2x dx. I can split them up into 2. This is easy. This is 1/2 x. That one's done. That part's done. And then I can go back and do the other part. If I want to do u sub for the second part, I can always do that off to the side. Let u equal 2x, du equals 2 dx. I don't have a 2 dx, so I do 1/2 du is equal to dx. Ooh, isn't that sweet? Look, I have a 1/2 dx. So I could clear this whole thing up, just that part of it, 1/2 integral, and I can put the 1/2 back inside, because I can do that. I can be in or out, in or out, in or out, doesn't matter, whatever I need for any constants. Cosine 2x dx, it becomes integral of cosine of u du. So I have the 1/2 dx, 1/2 dx, u for 2x, cosine of u. What's the antiderivative of the cosine? Not negative sign, just positive sign. Watch the negatives and positives with the sign. So this would be the sine of u plus c. So going back to here, take u, put 2x back in, plus the sine of 2x plus c. There isn't one particular method that's necessarily going to work every single time for everything. I don't have to do a u substitution for the whole thing. If I have addition or subtraction, I can break an integral up into parts and say, okay, what's the antiderivative of this? Oh, I can do that one all by itself. I can do this one all by itself. I can pull constants out. I can stick constants back in. Yes.
When you have 1/2 cosine 2x dx,
Right.
why do you still 1%?
Do you see what he's saying? It should be 1/4, not 1/2. Because I don't have this gets replaced with 1/2 du. So I should have this 1/2 still here, have a 1/2 and another 1/2 to go with the du for that replacement. So this should be 1/4 sine x. Yeah. Do you see what he's saying on that one? I got a little ahead of myself on that one. My bad. Thank you for catching my mistakes. Thank you for pointing it out while it's being recorded so everybody knows that I screwed up. And that my students are smarter than I am. Sometimes.
Oh,
Yeah, I've had students that were smarter than me. Maybe not necessarily at the time, but definitely in the future. I got a former student that's got a PhD in electrical engineering. Okay? He's smarter than I am. I guarantee that. Okay. I think that probably wins as the smartest or your most advanced degree that I have of a former student, a PhD in electrical engineering. That's up there. But I do have another one who's working with NASA. So that's the coolest one. Personally. Come on, go to the next. Go to. There we go. Okay. Do this one. Okay. In the interest of time, and not wanting you to feel tortured and anxious until we get back together again on Wednesday, let's finish this problem. So, first step, separate the sine cubed into the sine times sine squared. This is the integral of the sine of x times 1 minus cosine squared x dx is equal to the integral of the sine of x minus sine x cosine squared x dx, which is the integral of the sine of x minus, sine of x dx minus the integral, or actually I should, I'll leave it. Sine x cosine squared x dx. And this one, what's the integral of the sine of x? What's the integral? It's cosine. Negative cosine of x. That one's done. Now I'm going to finish the other part, and that one I'm going to do separately. We're going to need u sub for just that one. So I have the integral of the sine of x cosine squared x dx. just solving that one because the other part's already finished. Let u equal cosine. If I let u equal the cosine of x, du equals negative sine x dx.
You're not including the squared.
No, I'm not including the squared. And you'll see why in a second here. Because if I include the squared, I would still have a cosine in there. If I don't include the square, I don't have a cosine in there. Now, I have a negative here, so I actually do kind of have a negative cosine x. If I change this to plus and put my minus inside, that gives me minus here. Look what I have. I have minus sine x dx, minus sine x dx. So this becomes the integral of u squared du. What's the antiderivative of u squared? U cubed. So this becomes plus 1/3 cosine cubed x plus c. Remember, cosine squared is the cosine squared.
What about the square?
I did. I deal with the cosine squared. What happened to it? It's right here. Because remember, what is cosine squared x? It's the cosine of x squared. Right? Cosine squared is the cosine of x. Quantity squared. I let u be what's inside the square. I let u be what's inside because this is the cosine of x squared. I let u be what's inside the square. Give you another hint what your u subs should be. If you have something in parentheses raised to a power, let your u be what's inside the parentheses. Which is what I did here.
So that makes so much sense.
How did you get the sine cosine squared x, like the first, right?
I distributed.
Oh.
Whoa.
Now, I know a lot of you are going, oh crap, I am so screwed, I'm never going to get this. One, let me reassure you, neither I nor AP would ever ask you a question on a test that requires you to use an identity as we had on this problem and the previous problem. You will be asked that on your homework. They generally give you the identity to do the substitutions for. Okay, they give you the identity you need to use to do your substitutions. Other than the basic tangent is sine over cosine and cotangent is cosine over sine. That one you need to know. But the ones like this, you are not expected to have memorized nor used anywhere on an AP test or anywhere on any of my tests. But I do think this is a good problem to help you work on your manipulation, breaking it down, and working the problem out. Okay. We're almost out of time. We will